Well, good afternoon. I'm going to talk a little bit about what we see happening in the quantum market, really with a focus on the next 5 years, from 2025 to 2029. And let's see here. There we go. And the thing that we're always driving for, the thing we always want to see is, when will quantum computers be useful? And I'm calling that useful quantum advantage. And the way we see it, it really requires two things to happen both at the same time. On the left side there, you see quantum hardware. You always constantly see roadmaps. We've seen a lot over the past couple of days. The numbers of qubits are increasing, the fidelity of the qubits are increasing. But at the same time, there is developments in quantum algorithms, and in particular, more and more efficient quantum algorithms. And I'm going to talk a little bit about that, but sort of as you can see with the picture there, it's when those two meet. That's when people will start being able to use quantum computers for things that are useful. But we're going to need improvements in both of those things. To start, I wanted to talk you through what we call our frameworks at Global Quantum Intelligence. We see that quantum computing will evolve into various eras. Right now we're getting into the intermediate era where the way we measure these things is in QOPs, Q-U-O-P-S, which is quantum operations, successful quantum operations. And you can see that today we maybe do 1,000 quantum operations, and a quantum operation would be the number of qubits essentially times the depth of the qubits. As we progress throughout the years, today we're perhaps in the kiloquops era. As we progress through the years, we'll go to megaquops, then teraquops, and in the far future, 15 years from now, petaquops. To do something very, very complicated like Shor's algorithm, you're really needing to be in the teraquops area. And we won't see that in the next 5 years. But we do think that people will be able to get possibly to the megaquops era, and through the use of what we call early fault-tolerant quantum computing. And what this table shows on the left side there is the physical fidelity rate. And just to say where we are right now, some of the leaders are at 99.9%. A handful of companies have announced that. And where it says logical error rate on the right is where we could potentially get to with an error correction code. And there's some parameters about the error correction code in the middle there. But in terms of the roadmap, where we are today, we're basically entering the intermediate era. People are starting to build bigger and bigger NISQ systems. IBM talks about quantum utility, where it's processing certain problems, maybe not useful problems, but certain problems that can't be processed on a classical computer. But what we also see is that some companies are pursuing fault tolerance, what we call early fault-tolerant computing. So the issue we see, and that's really the focus of this talk, is the fact that if you're an end user in the next 2 or 3 years, you're going to be given a choice. Some vendors will be offering you a NISQ-based system that has maybe thousands of qubits, and other vendors will be offering you a fault-tolerant computer that maybe have hundreds of qubits. And which are you going to use? Both will be available simultaneously. When people talk about NISQ and FTQC, most people think that it's going to be a sort of an abrupt transition. NISQ will end and FTQC will start. That's not actually going to be the way it's going to happen. there's going to be an overlap between the two, and both will be available at the same time. Yeah, again, in this time frame, 2025 to 2029. As we move on in later years, we talk about things like large-scale FTQC and Goliath and mature, those types of things. And that will certainly happen in the 2030s, and that's, again, when people will start using these quantum computers for implementing things like Shor's algorithm. So here are some of the challenges that we see, that problems that people have to solve. That right now, the biggest problem is, of course, there's too few qubits, and the fidelities of those qubits are not good enough. People have implemented small numbers of qubits with qubit fidelities of 99.9%, and then when I talk about that, I talk about 2 qubit gate fidelities. But there's a lot of technologies they need to develop to build the larger and larger computers. For example, one thing that we've been studying is how do you scale quantum computers by networking multiple modules together. We had a number of talks today over the past couple days about that. That will be a key technology for some of these larger and larger computers. And how do you control those? So there's a lot of work that still needs to be done, and this is sort of a slide that shows the framework of what we track. On the left side of that slide is what we call the quantum stack, where at the very, very bottom, actually just the simulator is a software thing, but if you look at the quantum plane, that would be the chip where the qubits are. How do you control that? What is the firmware that controls those chips, to the framework and the software and the architecture, all the way up to the applications and end users. And there are developments all up and down the stack. And we've seen that in the past couple days. Many companies are working at various levels there. So one of the things we have at GQI is we see many roadmaps from vendors. They publish them. Some are public, some are not public, but we see those. And we have been able to generalize what we see and what we forecast. Those are 4 that basically have been made public so far, between IBM, Quera, Inflection, Pascal. I think actually Jay Gambetta showed IBM yesterday, and we saw the Quera one earlier this morning. So there are a lot of roadmaps. Companies are talking about that. And again, if you look closely at some of those roadmaps, some of them show fault-tolerant quantum implementations. Others show NISQ implementations, particularly in this time frame that I'm talking about. So again, if you're an end user, at the end of the day, you're going to have a choice. You're going to have a choice between a NISQ machine that may have as many as 10,000 physical qubits with, pretty good fidelities, 99.9%, maybe 99.99%, or you're going to have fault-tolerant computing systems available that maybe have 100 or 200 logical qubits, but the fidelities are going to be a lot better, 5 or 6 nines. As you can see there. So one of the questions that we see that's constantly argued in these conferences, and we actually saw a little bit discussion today from BCG, is whether people are going to be able to do anything useful with a NISQ machine. It's certainly true that the expectations are perhaps a little bit less than what we thought 2-3 years ago, but they're not zero. There are still applications that we think potentially can be run with these NISQ computers. So that's the question the end user is going to have. But I just wanted to cover a lot of the work that's being done by people in order to improve their system and make them better. There's a lot of work being done, of course, in hybrid classical quantum computing. Can you come up with algorithms where perhaps most of the work is being done by the classical computer and only a very small portion of it is done by the quantum computer, but it's very, very important portion of it. Those are called, those are, a lot of people are working on those. There's a lot of activity with variational quantum algorithms, VQE, QAOA, where you're constantly cycling the algorithm and the data back and forth between an ansatz that's set on the classical computer, it's given to the quantum computer evaluates it, and you go over and over again with perhaps thousands of cycles until you come up with some type of thing that's optimization. A lot of work being done in error mitigation, error suppression technologies. We saw companies like Q-Control, for example, and Kedma talking about ways that they can use their quantum control technologies to make the quantum computers better. But there's also error mitigation where you can perhaps come up with a quantum circuit, you can run it multiple times, and then analyze the results from all those times on a classical computer at the end and come up with a way of sort of minimizing the errors. So there's a lot of work there. One thing that's very interesting that IBM is exploring is something called circuit knitting, where you may have a very large quantum problem. The problem itself won't fit inside, the specific quantum processor you're using, but can you divide it in pieces? Can you process each piece separately, take the results, and then combine those results again in a classical computer towards the end? So there's a lot of work to make the NISQ machines that are to get them to provide useful results. And in the meantime, there's a lot of research and reports on fault-tolerant quantum computing. And I would say that the results that we've seen within the past 12 to 18 months is actually faster than what I initially expected. We heard about the 48 qubits at Quira and then Harvard did, but there are many other things that people are talking about to accelerate error correction. A lot of demonstrations within the past year that would indicate that error correction is coming a lot faster than we thought. There's things like mid-circuit measurement, which will help for error correction. And the other thing that we see is new error correction codes. 2 years ago, people were saying probably the dominant code will be something called the surface code. And within the past year, 18 months, people are now talking about a more efficient code called quantum LDPC. That's low density parity check. And the advantage of QLDPC is the fact that it reduces your physical to logical ratio. Rather than using perhaps 1,000 physical qubits to create one logical qubit, maybe you're down to 20 physical qubits for one logical qubit, because that certainly would help you fit more logical qubits in a given size machine. So both of them, again, we're making good progress. Both of those will be available. I would say that people do have fault-tolerant quantum computers, we do expect they could also process NISQ algorithms, but we'll have to see. But it's important to understand that it's more than just the physical design. It's more than just the qubit chip itself. It's all the control logic and the control firmware that is important also to make the machines better and better. But on the other side of the coin is the algorithms. You have to make the algorithms better. And actually, one of the things that our host here at QCware does is they have scientists who figure out ways of implementing their algorithms with fewer qubits and fewer levels of qubits. So we're seeing more use of AI to do things like transpilation, make the circuits more and more efficient. We're also seeing improvements in terms of the quantum runtimes to make the classical computer and the quantum computer, if they work together with smaller latencies. So if those two work together, you can still process it very fast. So speed of operation is going to be very, very important too. And again, quantum algorithms also need to improve, and we've also seen a number of talks over the past couple of days where people talk about what they're doing in those areas. So we are tracking a lot of work that is being done with improvements in quantum. There are heuristic algorithms where people can't necessarily prove exactly that it will work, but they try it out. And if you think about it, AI is like that today. People don't exactly have theoretical proof why something like OpenAI should work, but they tried it and it does. So of course they're using it. But there's a lot of techniques again that we're tracking today to make the software better and make it even more efficient. So and the other thing that I would also mention is when we talk about quantum advantage, the bar does raise year after year because classical computing is continuing to get better. People talk about the fact that Moore's law is coming to an end, but don't let that fool you, because it is certainly true that at the transistor level, the progress of generations of transistors is slowing down a little bit, but there's still a lot of innovation with regard to computer architectures, all the GPU architectures, for example. There's a lot of people building larger and larger machines. I know the biggest machine here in Japan is Fugaku, but there's bigger machines that are planned elsewhere with millions of cores. So the classical computers are still improving, and people are improving the algorithms also on the classical computers too. So when you talk about quantum advantage, every year the bar gets a little bit higher, and that's the key. Is the quantum solution has to work out better than the classical solution, or else people just won't use it. So the summary is everything is improving rapidly. There's a lot of different approaches. Different vendors are taking different approaches to what they're offering and what's available. We do think that there may be some possibilities for NISQ algorithms to be run usefully over the next few years. But that really large things like Shor's algorithm or quantum chemistry type of things, those require what we call the teraquops type of solutions, and those we will not see within the next 5 years. But users will have to figure out for themselves, and it will all depend upon the use case. So, but it will be a very interesting time because of all the different things that are happening. So if you're interested in hearing more, our company, GQI, Global Quantum Intelligence, has a number of reports available. We have one on scaling quantum hardware. You can see the website. You can go to global-qi.com. And we have a full team behind this. We work very closely together. We work closely with our clients to provide solutions in terms of a number of ways. So with that, I thank you for your time.